think there's a lunch or two left. Yep, there you go.
And a sign-in sheet. This is SEAAK.
Oh.
See, we got lunch too.
All right. SIDEPLATE Moment Frames. No? Okay. Right. All right. Yes. Thank you. So why use moment frames in general? You know, and I think that those of us, we're all structural engineers, we're nurses. I think we understand why we might use moment frames. The main ways to hold a building up, laterally speaking, you've got brace frames, you've got moment frames, you have shear walls. It kind of comes down to one of those three things. Moment frames are great because it gives you a wide open floor plan. It gives you a lot of flexibility. And so that's one of the things that that we're always fighting on the engineering side when we have shear walls and brace frames. Where do we put them? Where do we hide them? And invariably, we'll have an architect that wants to give us a floor plan where there is no opportunity to put one in without making somebody angry or without putting something in the way. Moment frames really get out of that because you have larger columns, but still it's just a column. And architects are really good at working around columns, and they don't mind when columns end up in the middle of certain spaces. But brace frames and shear walls do create issues, and not just for the building that we're designing today, but the building that will become in 30, 40, 50 years when they do a remodel, an addition, renovation, you know, or even a mechanical gut and redo. You'll always find that they're running into braces and shear walls. We do a lot of work at Providence Hospital, and there's this sprawling set of plans of all these different renovations that have happened through the years. And more than once I've seen happen where we have this plan of what we're going to do. The contractor gets in there and opens up a wall and says, there is a brace going right through the middle of our new OR. What the hell do we do? And so that doesn't happen with moment frames. So the other thing that they allow you to do, since you're not concentrating your lateral force resisting system in these discrete areas where you've got shear walls and brace frames, it can result in lower impact to the foundation. So if you've got crappy soils and you're trying to work around that, you can do that a little bit more effectively sometimes with moment frame. What is a moment frame? I think we all know what a moment frame is. If you don't know what a moment frame is, raise your hand. If you're online, you're out of luck. Let's move on. So 1900s to 1960s, the moment frames were mostly built up sections and rivets. We don't do that anymore, but I think we all understand you've got a rigid connection and you know, no diagonal members, and the rigidity of the column, the beam, and the connection all play into the response of the moment frame. Slide. So back in the old days, things were great. Things were easy. Okay, if you had a moment frame connection, all you had to do is just weld the puppy up. You get a beam, you get a column, weld the hell out of it, and you got yourself a moment frame. You know, as codes changed, you might have pushed on these a little harder going on through the 60s, 70s, 80s, 90s. But in essence, it was still a pretty simple situation. A lot of moment frames, especially for larger buildings with heavier loads, were all welded. And you do a field CJP weld for your beam up against a wide flange column to develop basically a fully rigid connection and develop the capacity of the moment strength of the beam into the connection with the column. So that was all well and dandy up until the 1994 Northridge earthquake. And so when that happened, you know, moment frames really took a hit. That was sort of why we still feel today that we're a little cautious in recommending moment frames for a project to an architect or to especially a contractor. They're like, oh, we don't want moment frames, they're too expensive. You know, well, that's like the general consensus. Don't do moment frames, they're too expensive, it's too costly in the field. The reason that sentiment exists is because of this earthquake and what was learned in the 1994 Northridge earthquake. Just in time. Thank you. Bye. So, interestingly enough, there were quite a few structural failures in the 1994 Northridge earthquake. It was a moment magnitude 6.7, which, as we all know, I mean, come on, that's nothing. We did a 7.1 a few years ago. I mean, now that was an earthquake. 6.7, a big deal. Lasted 10 to 20 seconds. Okay. There were a number of structural collapses associated with the Northridge earthquake. And you can see some of them here. We've got an actual collapse here of a parking structure, and then an office building with a significant amount of structural failure going on through the building. Interestingly enough, there were no failures, there were no collapses of moment frame buildings in this earthquake. However, of all of these seismic systems available at the time, no system was impacted by this earthquake more than moment frames. And so, go ahead and slide. So there were a lot of failures of connections in moment frame buildings. They didn't result in collapse, so that's good. But the idea being, this was not a very big earthquake. And if it had been a bigger earthquake, we would have seen across the board issues with this particular structural system. What you had in pretty much all cases where you had damages, you had fracture somewhere in the weld between the beam and the column of these large steel moment frame connections, okay? You had ruptures of the bottom flange weld, or where it joined the column, or cracks in the column flanges. But basically what was determined is that this system might have the strength that we designed it for, but it does not have the ductility that it needs to respond to an actual earthquake. And honestly, it kind of took moment frames off the table for a while. Slide. So we had a major overhaul of how moment frames and their connections are designed, evaluated, and used throughout the country and the developed world that uses, then the UBC and piggybacking into the IBC at the turn of the century, like saying at the turn of the century. So after a multi-year study, they changed the code, okay? And the way that they changed it is they said, okay, you can use moment frames now, but they're going to be very, very expensive. And honestly, that's still the case. Even though I'm going to talk about SIDEPLATE, how I think it's a great solution, it still is a lot more expensive than the old way of just welding a beam to a column. So, go ahead. So this was sort of the first generation of available moment frame connections that we had for steel buildings. And they range from kind of suck to really suck. So we'll talk about them briefly. You've got the end plate connection and the bolted flange plate connection. Those are in the kind of suck category. This one, I would say, sucks more. But reduced beam section, or the dog section, I think we can all say really sucks. It's very expensive in a number of different ways. And frankly, I saw those connections going out the door of one of our projects, and I wanted to go smack the guy that drew it up against the side of the head, but I didn't do that. It worked for that building, but it's one of these things that I would say I've never used them, and I don't ever want to use them, but I think that there's just a better way. These bolted end plate and flange plate connections, they have their place. Has anybody ever used those before? They are pain. They're very rigid in terms of what geometry you can use them for, and what the maximum beam size that you can use for a given moment frame. There's a lot of requirements on those systems, and sometimes it can make it really hard to get them to work. And you can sort of chase your tail. You start at one spot and that doesn't work, and then you make something bigger and that doesn't work. And then pretty soon you're just like, okay, I'm out of options. I've got to do something else. I've got to incorporate another frame into my moment frame. And so, but they do have their place. Another issue that you have with these types of connections is that they've got a lot going on over the top of the flange of the beam. You've got this plate here with these bolts that get in the way. Here you got a stiffener that gets in the way. Here you got this entire flange plate that gets in the way. So if you've got a floor or a roof, it's a little easier to deal with the roof. You support the deck around the connection, and then all the stuff that's happening up on top gets lost in the insulation, and that's not that big of a deal. But when you have a floor system, it gets a lot trickier to try and work a floor system around all that stuff. And you end up growing the column encapsulation to hide all of that junk. So those are some of the downfalls of those connections, but they do work and they do have their place. As far as the reduced beam section, RBS or dog bone connection, you're not really saving anything because you still have a field welded connection. So it's like you're getting it for the cost, the same cost as your original welded connections back in the 90s, right? But you've got a lot of extra cost associated with this connection where you have reduced the beam section with a radius cut. And it's very particular how that cut needs to be made so that there's no opportunity for spikes in stress as you push this thing into plastic behavior. But the biggest thing about them is that they make the beam not as stiff, which means it makes the frame not as stiff. And for anybody that's ever done a steel moment frame building design, you probably know pretty quickly that you don't design them for the strength that you need. You design them for the stiffness that you need. And this is a stiffness killer. So all it does is it drives up your column sizes like crazy. You get a really big beam size and then you cut a third of it away. And it's just a really expensive and messy connection. I think this was the industry's first response to, we want a plastic hinge here. We're going to make it happen by literally cutting the beam. This is going to work until we can find something better. But that is a segue. Let's move into side plate. Okay, so side plate came around on the scene really probably about maybe almost 2 decades ago, but really more like a decade and a half ago. So probably about 2010 is when they really started to say, hey, we have all of our ducks in a row. We've got a product that works. Here's what it is. And so we had a guy come up and talk to us about it. It was sort of one of these, oh, that sounds cool. And we kept it in the back of our heads until we had an opportunity to use it not that much later. And we said, hey, this really does work. So the basic idea behind side plate is you have this set of plates on either side of your connection, okay? And it basically takes the connection and pushes it out into the beam so that you've got a tremendous amount of additional strength right at the connection between the beam and column from this added reinforcing provided by the plate. You also have the opportunity for ductility to happen within that plate. They've tested this throughout the process over and over again to show that they have the ductility. And you also have the ability to develop plastic hinge in your beam without causing any sort of brittle or fracture failure in your beam because your beam extends into the plated connection a certain. And so that is kind of the long and short of their system. They either have a field welded connection system, which is shown on the left in this slide, or they actually have an all field bolted connection where there is no field welding and it's just all bolted. But one of the things that they wanted to have from the very beginning is no CJP welding, no groove welding in the field. So even their welded connection system only utilizes fillet welds in the field, which helps to take the field costs down. So go ahead. It meets the requirements of IBC code families. Of course it does. Otherwise we wouldn't be seeing them in Anchorage. And so, yeah. So side plate is a proprietary system, but it is not a product. And this is where it's a little bit interesting, and it's different from things like buckling restraint braces. Buckling restraint braces, I know that a lot of you have used those before. I know several of you in the room have. Buckling restraint braces are basically provided by a number of manufacturers that say, here's our product. We give you a product. You design a BRB and we will supply it. We'll help you design it. And we've got our people that build it, and it's a product. And it's basically like a copyrighted product, okay? Side plate doesn't have any sort of product. What they provide is a design method and a set of construction documents. And then every single component of the side plate system is fabricated by any normal, regular steel fabricator. It's detailed by the same detailer that would otherwise be doing your project. It's fabricated by the same shop. It's just made up of plate and angle and bolt and other regular types of materials that you would find. There's no proprietary product. So the way that it works is they provide drawings and calculations. They also provide design assistance. They will work with you on the project as you go forward. And I'll talk about that a little bit later. They actually charge the fabricator for their fee. They'll look at a project and they will come up with a fee, however they do it, probably similar to the way we do it. They look at the value, whatever. They They have a fee and they bill the fabricator. So the fabricator is actually the one that pays SIDEPLATE. So they will review the shop drawings as well as you. They will attend things like the pre-fabrication and pre-erection meetings and maintain some sort of contact during erection. And they will do field inspections and inspections of the shop that is fabricated. All bolted connections. The first connections that they had that hit the street were the all welded, the not all welded, but connections that required field welds. But they were working hard to get the bolted connections online. And once they did, I think that since they had those approved the same level as the welded ones, we have only seen them use the bolted connections. I mean, it's a no-brainer. There's more angle and material and stuff associated with the bolted connections, but you're obviously going to save costs if you have bolted field connections instead of welded field connections. Move on. So versus other moment frame systems, this is just kind of here's the same slide that you saw before, but just for comparison. They are stiffer connections than any other system, which I think is pretty easy to visualize. You've got these large plates that encompass the entire connection, so it makes the connection stiffer. There's no CJP groove welds. I think even the welds that they have in the shop are fillet welds for the way that they typically put their connections together. So those really large CJP welds that you would have to these really heavy beam sections, you don't have that. I mean, some of these beam sections you can have like a 10 or a 12 pass groove weld. That is an expensive weld to do, whether it's in the shop or in the field. And so, so a lot less welding for these connections. They have higher ductility than all other bolted connections, which means that they can go into the plastic range and have plastic deformation back and forth, and they've got a really strong hysteresis performance, superior to the other connections. And then, of course, I just basically took this opportunity to take another rip at RBS connections and just say, basically, yeah, they still suck. But to the first part of it, stiffer connections, but also stiffer systems, because another thing that you find is that when your connection extends out into the beam, the code actually allows you to reduce the length of that beam when calculating frame stiffness. And so that further helps increase the stiffness of your moment frame, which means that you're going to end up with smaller sizes. So there's pretty much advantages from top to bottom with something like SIDEPLATE. And some of the design software that we use Bentley RAM Structural System to design buildings quite a bit. And they have a plugin for SIDEPLATE that allows you to put some additional information in, and then it will actually do that process where it uses a shorter beam length, I think a shorter column height, in calculating moment frame stiffness, so that you can capture some of that economy and end up with some smaller sizing to get your building within the deflection limits. So I'll go ahead and talk about a couple projects. This of course, so this one didn't win us any awards, but that's okay. It's a U-Haul self-storage. We all need to store things, right? This project is notable for a couple of reasons. First off, this was our first project that we used SIDEPLATE Moment Frame. And until somebody corrects this statement or challenges this statement, we do believe this is the first SIDEPLATE Moment Frame project in the state of Alaska. So this was back in 2014. And the further interesting part of this whole process is that we were not the engineer of record for this project originally. U-Haul, like some of these other national companies, in their wisdom, said, we've got a guy who's licensed in Alaska as part of our typical design suite, and he lives in Arizona. So what about Alaska can this guy not know, right? Turns out there's a few things that he doesn't know about Alaska living in Arizona, even though both states begin with A. So just the basic rundown of the facility: 3 stories, completely open floor plate, so no brace frames. They didn't want to have any brace frames. It's 76,000 square feet, so it's a pretty big facility, and a couple things hanging off the side. Here is just kind of a basic rundown of the original framing plan for the building. And I guess to kind of keep going with the story, so they submitted to the Muni, and I'll get to kind of a specific timeline in a second, but basically they submitted to the Muni, and I don't know if Daniel, I don't think you were there quite yet, because it's back in 2014, but Wayne and some of the other guys there took a look at it, and they issued a number of sheets of comments. We've all seen that before, but this was pretty bad. It was basically a tongue lashing, like, hey, there's all these problems. And essentially, after several rounds of back and forth, the original designer could not resolve the comments and had kind of basically just been like, I've never had to deal with this before. Why don't you just give me my permit? And as we all know, how often does that work at MOA? No, we don't care what you've done before. So in any event, we were called. It was kind of one of these things like, hey, guys, we need some help. All right. So the original design was submitted to MOA in July of 2014, July 1st. Initial comments came back on the 14th, 2-week turnaround. That's good. It was almost an entire month went by until August 12th when additional comments came out. And before any responses came in, a month later on September 16th, additional comments came out. Like basically, so there were unresolved structural issues as of 9/16 that the moment connection to weak axis of wide flange columns was not permitted. So basically, they had moment connections in 2 directions coming to wide flange columns. Well, you just can't do that in seismic design category D. You can't have a moment connection to the weak axis of a wide flange. They had strong column, weak beam requirements that they had not met throughout the building, and others. There were a lot of problems with this discipline. So we were called, I think, something like a day or two after that. Go ahead, slide. So we were called, and I'm not sure, I think it was Colin that basically said, hey, we heard about SIDEPLATE. This is going to be a mess to have to design using the other systems that we have available. I think even at that time, some of the other bolted connections, the bolted end plate and the bolted flange plate were pretty new. And we had used them and they just kind of seemed ugly. So we called SIDEPLATE, and we got SIDEPLATE on the phone, and they basically said, yeah, this is a great candidate. It's a regular building. It's repetitive, 3 stories that are exactly the same. Like, this is the project where we could jump in, work with you guys, and we could get this thing banged out. And we said, okay, let's do it. Right. So they hopped in. We put together an ETAPS model of the building, and we sent that to SIDEPLATE. And you can send them your entire model. We send them a RAM model. We send them ETAPS models. Whatever we're using for design, we can send them. They can talk in that language. They'll make some changes, send it back, or they'll talk us through some things. But they provided general notes for the connections and connection schedules and connection details. We provided everything else. We threw out the old set of drawings, and we created an entire new set of drawings, gravity design, drag struts, moment frames, so on and so forth. And again, the fabricator paid SIDEPLATE's fee. So go ahead and hit the slide. So this was the original moment frame layout. As you can see, it's basically a grid. It's every structural line is a moment frame, which is not probably the most efficient way to do anything. So we got together with SIDEPLATE. We worked out this moment frame layout, which, as you can see, is a lot more discrete and frees up. We ended up saving a lot of money in the framing throughout the building, because when every single beam is a moment frame beam and every column is a moment frame column, you're going to pay needless costs. You can skip through this, just those are the moment frame elevations. And this is basically this is the actual sheet that SIDEPLATE provided. And so they've got this schedule for their connections. They've got kind of their standard details, but this basically just folded into our set as part of the construction documents, and it went to the fabricator, and they built it off of this stuff in conjunction with our stuff, just as they would any other building. So back to the project timeline. I had taken you through to here, additional comments. We came in on that day. On the 16th, we started our value analysis. 3 days later, we sent our ETABS model to SIDEPLATE. Fast forward a couple weeks to October 2nd, we got a new design submitted to the MOA. So basically, in just 2 weeks, we were able to take this from, oh my God, we need your help immediately, to submitting to the MOA using this new system. We got initial comments back from, I think, Wayne, 1 week later. We got an F&F permit approved 5 days later, final comments on the 22nd, and a full permit on November 7th. So in less than 2 months of us hopping into a project that was completely stalled out, using SIDEPLATE, we were able to get the full. So yeah, savings. Now, this also ended up saving, of course, it made the project happen because it was stalled. But we also wanted to take a look at what we'd saved. So we originally had 65 columns. We ended up with 67 columns, but we saved 54 tons of steel in the process because they had 124 tons of columns and we ended up with 70. Beams, we ended up with a little bit more beams. It says increase in number was primarily due to using steel framing for the port share and elevator cap in lieu of light gauge steel framing. So that's not really fair necessarily to look at. But even as such, we went from 273 tons of beams to 211 tons. So we saved 62 tons. CJP welds, there were 1,260 CJP field welds in the original design. 1,260 CJP field welds. The revised number, of course, was 0. Fillet welds, they didn't have any fillet welds. We ended up with 552 fillet welds in our site. I mean, just in terms of number, obviously there's fewer welds, but to swap 2.5 CJP welds for every fillet weld, we obviously saved a pile of money using site. And that includes special inspection time as well. Obviously, special inspection and testing of CJP welds, as we all know, is onerous. So we're doing good. So SIDEPLATE's fees for this project were paid by the fabricator, $38,000. You know, for a $76,000 square foot building in 2014 dollars. That just gives you an idea of how that tracks. It's not cheap, but it's not. You know, I think that they typically can demonstrate that they provide savings well in excess of the fee that they charge. And we already talked about what they do. They did 2 site visits during erection and 1 to the shop during fabrication. And erection was completed the following spring. So a couple other SIDEPLATE projects that we've used just to kind of give you an idea of the variety of project and scope that we can use this for. This was one of the smaller projects. I think it just had a single SIDEPLATE frame. It was in addition to the Bartlett High School cafeteria. And so it's a single story structure. And honestly, this is the kind of thing that I was a little surprised that it was a good candidate for SIDEPLATE. But, you know, there was, we evaluated 3 different lateral systems as things went forward. But when SIDEPLATE was suggested, they were very responsive. They came back and basically not just told us, but showed us how they could be competitive with the other systems. And the SIDEPLATE bolted, this was our first time using the SIDEPLATE bolted frame connection because the bolted connection wasn't quite available when we had done the U-Haul project. Slide. There's a picture of the completed structure. Oh, wonderful. And it went through the 2018 earthquake with no visible damage. So, you know, that's good. This is the Norton Sound Health Corporation Wellness and Training Facility in Nome. You know, just to show you that these do have a place to work out in western rural Alaska locations. Pile supported, it's elevated on piles. And so large facility, and again, wellness and training facility is the kind of thing that this building is probably going to see multiple renovations throughout the years. They're going to play with the floor plan. They're going to probably add to it, do things to it. And so that was part of the reason that we said from the beginning that we think this is a good candidate for moment frames. And if we do use moment frames, it's a good candidate for SIDEPLATE moment frames. So piles were driven in 2018, building erected in 2019. SIDEPLATE assisted not just with the design, but they you know, when they get involved in a project, they look at the building and they help the structural engineer figure out where the frames need to go. So they'll look at your layout and you can say to them, hey, these are where the frames are going to go. And they'll say, okay, well, that's fine, but we think that you should at least look at putting some, you know, here and modifying it. And so they really do a good job of working with the designer to locate where the frames are going to go and then collaboratively design. So we use the bolted connections for this. Basically, since they brought the bolted connections online, I think that's all we've used. So there's some pictures. You can see here the bolted connections of the side plate frames. And, you know, it's funny, just from looking at the frames, you see they're not quite as big as in Anchorage. You know, we're out in Nome. It's wind governed. We've got some seismic, but yeah, it's always funny. If this were in Anchorage, it would all be a lot bigger. But yeah. So more recently, we've got a medical office building that is, I think they just completed it last year for SEAAK or SEAAK. Yeah, SEAAK they call it. Southeast Alaska Regional Health Corporation. 3-story medical office building, and it's got side plate moment frames. It's got a lot of features, a lot of architectural features going on. You've got this curved facade in the front. You've got canopies that come in at different levels, and we weren't sure how that would work with side plate, but again, we built a model in RAM that utilizes, you know, that has the structure exactly as you see it. They were able to take that and work on it and work with us through the design, and we completed the project. So some pictures of it going up again with the bolted moment frames, and then this is something that is, you know, the indicating the protected zones on the connection. And so we're all familiar with that. But yep, that project went well, went up. There were no issues. You know, you worry sometimes with complicated connections like this, the fit up issues that you might have in the field. And what we've found is that between the notes that we put on there to verify fit up in the shop before it gets shipped to the site, and just the quality of contractors and fabricators that we have for this type of project up here, we haven't run into any issues where something shows up in the field and they're like, this just doesn't fit, we got to hit on it with a hammer. So, and then finally, Daniel was asking me about this before the meeting. This is the sprawling South Central Foundation Tudor and Elmore development going up currently at Tudor and Elmore. It's right kind of behind the Ernie Turner Center. So this was an interesting one because it's got 2 levels of parking and sloped deck to get, you know, into the parking areas. But the parking areas are worked into the floor plan of the building. It's not like you have parking on the bottom and then office building on top. You've got office building over here that sort of surrounds the parking area that then just turns to office space above. Like, so the 3rd floor is a consistent 3rd floor, but the 2nd floor office kind of cuts through parts of the sloped parking area. So it was definitely going into new territory for trying to work with something like a side plate moment frame system for something that's got such a unique and irregular lateral characteristic. But again, we put our minds together with them. There was a lot of back and forth. We shared models. We talked about dynamic responses to this building, and ultimately we designed it with the side plate moment frames, and it's currently being constructed that way. So there's some pictures of the construction. You can see here in Anchorage, we got some larger connections and some columns associated with our lateral force resisting systems. But you can see the parking deck ramp going up and coming back down, and you have this level here and this level here where you've got, I don't know which one's parking, which one's office, but you know, complicated geometry and complicated structure. And we were still able to get side plate to work. So for kicks at one point, I actually, this part of the presentation I used to sell it to a design build contractor, and it worked. This is an actual, it says example project, but this is an actual project that we did at BBFM. And this was before side plate moment frames were on the market. This was back kind of in the mid 2000s. So we didn't have side plate moment frames at our disposal. And we had this 8-story office building. And basically we felt that there wasn't really a viable moment frame system to use. So we went with special steel concentric brace frames, all located in the core of the building. And so this is a snapshot of the RAM model that I built. And you can see all of this jungle of steel in the core of the building that makes up the lateral force system. So again, this project was built. This is a model of the building that actually exists today. So what I did after the fact, once we did have side plate and we had used it, this is actually after we had used it for U-Haul, I said, what if we had been able to use this for this building? And so I created a new model of the building using side plate moment frames. And side plate actually, they agreed to play ball with us. They said, yeah, let's do this. You send us a model, we'll do the thing that we do. We'll send it back to you as sort of like a dress rehearsal type thing. We'll even tell you how much it would cost if we were doing this building. So they decided just kind of for the purpose of marketing this to design build contractors and other people, they'd go down this road with us. So here's the model that I made. And as you can see, I've taken the moment frames and I've pulled them to the perimeter of the building, leaving nothing in the core of the building except gravity. So right off the top, we were able to have a 33% reduction in seismic forces because we have an R of 8 versus an R of 6. Now, granted, this is back, those R values I don't think are, I think they've modified a little bit since then. This is 15 years ago. But so we took 33% right off the top, going from an R6 to an R8. We've got open bays now in the core of the building. Now, granted, they don't typically reconfigure the core of the building because you get your elevators and your stairs there, but all the same, you do have a lot of mechanical that goes down through the core and mechanical shafts and ductwork coming out at all levels. And now you've just got all kinds of open space to deal with that. Frames at the perimeter versus in the core reduce the torsional effects and drag strut diaphragm loads. And we'll talk about that a little bit more in a second. And there's a lot fewer steel pieces. So you can actually just tell by looking at this, all we've done is remove pieces. Every single moment frame beam and column in this version of the building exists in this version of the building. They're all still there. They're just a little bigger as a moment frame than they are as a gravity frame. But all of this junk in the middle of the building is just gone. So there's a lot fewer steel pieces in the moment frame example. So torsion, again, speaking to a room of engineers, as we all know, when you have a lateral force resisting system that is grouped tightly in the core of a building, even if it's symmetrical, even if your building is symmetrical, you're still going to get a lot of torsional activity in that building because you just have a very large building that you're all resisting laterally from the center, and it's going to be able to twist quite a bit. When you go to moment frames and you take those to the perimeter, you really, really dramatically stabilize the building. And of course, it went from having an extreme torsional irregularity as a steel brace frame building of the core to not having a torsional irregularity at all as a moment frame building. And so let's see here, trying to figure out where it's, so basically sum of all internal forces, including torsion. This just basically shows that this was the total sum of all of the brace frame loads for the steel brace frame building, and it's 3,000 kips. Now I did do a run at this using the same brace frame layout, but using BRBs to show that those also provide a savings. And so again, BRBs, you take that 33% off the top in R value going from 6 to 8. So you do have a reduction for BRBs going from 3,000 kips to 2,200 kips, but the total sum of all of the forces in the moment frames for the moment frame option was 857 kips. So that's the same R value from BRBs to the moment frames. It's the same R value, yet the total force in all of the braces for the BRB version is like 2.5 times what it is for the moment frames. which simply means that you've got a lot of forces developing in your brace frames due to torsional effects. That's what that really means. Because the weight of the building doesn't change. So this was the original column schedule of the building, and I know you guys can't really read that, but that's okay. I'm glad you can't, because we're using the largest size W14 columns in the book. And if that isn't enough, we actually had to specify grade 65. This is a 14 by 605. It's a 14 by 605 grade 65 steel in order to get the columns to work for the original overturning forces that we had in the brace. So just absolutely humongous columns all throughout the core of the building. So I think the next slide is basically the revised column schedule. And the heaviest column that I have is, I think, a W12 by 207. We've gone from a 605 to a 207. And that's at the perimeter now, since we're looking at moment frames at the perimeter. Every green highlighted column that you see, there's a column that was actually deleted. Because when we went from brace frames to moment frames and took things out of the core, we didn't have to have all these columns to complete the brace frame where, okay, the brace frame could be here, but it has to stop here because we have a hallway, or we have a duct chase, or we have an elevator or something else. So we actually were able to completely eliminate, I think, 5 columns from the center of the building. Now foundations. The foundation plan for this building is crazy, okay? This yellow line shows a mat slab at the core of the building. You can see all the brace frames oriented here. And again, this is how this was actually constructed. If you go to the next slide, you can see we have a 6'6" thick central mat foundation with a little bit of reinforcing in it, as you can see from this diagram. This is just the plan for the extent and reinforcing of the mat slab at the center of the building, supporting that core with all those brace frames. It's absolutely humongous. It took an entire day for them to place it with concrete trucks, just one after the other, showing up and dumping mud. It was huge. And that basically, in the moment frame example, is completely gone and replaced with spread footings at the columns. Just your typical kind of, the spread footings are big. It's an 8-story building, but I think they're 14-foot square, something like that, 2.5 feet thick. Really nothing compared to the mat slab that they put in. Now, what about what's supporting the moment frames? The original construction, I think, had a 2-foot wide grade beam around the perimeter to support perimeter gravity columns. Moment frame version, I was able to work with, I think, a 3-foot wide, 2-foot thick grade beam around. So again, it's not really that much bigger than what's there. And it still is driven largely by gravity loading, not lateral loading, as opposed to the central mat foundation, which was obviously very heavily governed by lateral contribution. Now, when it comes to the floor framing plan, one of the things that also added a lot of cost to this building is these drag lines, our collectors, okay? As you can see, we've got 4 collectors in the north-south direction, 2 in the east-west direction, and they're all inside the building, which means they got to cross. And at each one of these intersections, we've got field welding, we've got really difficult detailing. You know, when you have a drag line that you're developing through a connection, as long as it's only in one direction, you can deal with it a lot easier than if you've got to get it across. And so very extensive field welding for our drag struts to get the loads from the diaphragms to the brace frames and vice versa. Now, clicking ahead to the moment frame example, obviously, it's just all around the perimeter, and it's a lot smaller of a force, and it's a lot easier to work because along any line, you just have one direction to work. And again, the green dots are those columns, like I said, that we were able to eliminate. I said 5, and I was wrong. It looks like we eliminated 9 columns, or we would have been able to eliminate 9 columns completely. So here again, you got your brace frame elevations on top versus what those elevations look like in the moment frame example, with the green showing you where columns are just. And as far as these brace frame elevations are concerned, we had a lot of places, this is the core of the building, we had a lot of places where we're trying to work ducts through the openings in these brace frames. And we fought it every step of the way, as opposed to moment frame example, no problem. You can skip this slide. And this, of course, just shows you some of the detailing that we have for this project. We had these very expensive column-based details where we had basically a second bearing plate above the base of the column with these fins that are needed to basically resist just those huge uplift forces that we got at the base of these 8-story brace frame columns. Your protected zones, your bend lines, all that stuff. It's just all very expensive detailing. And it was replaced, it would have been able to be replaced with just your side plate details, which are just a lot cleaner, a lot easier, especially when you're looking at column pieces. So you can just skip through this. We've seen that. So material savings, I'm just going to run through this. And again, this is hypothetical, but it's still, we did have side plate play ball with us and help us generate these numbers. So we've got special concentric brace frames, buckling restrained brace frames, and side plate. Total steel weight of the building, 3,400 kips, okay? We feel that if we had BRBs, we would have been able to reduce that to just under 3,000 kips, save a little over 400 kips of steel. But with side plate moment frames, we would have been able to get that down under 2,500 kips. So concrete, again, the building had about 2,200 cubic yards of concrete with 292,000 pounds of rebar. We could have reduced that a bit to 2,060 cubic yards of concrete and 241,000 pounds of rebar with BRBs. But the ability to remove the central mat slab for side plate, we would have been able to reduce it down to 1,480 cubic yards of concrete and 109,000 pounds, 109,000 pounds of rebar. So 2/3 of the concrete volume, 1/3 of the reinforcing weight, if we had gone with side plate moment, if we had been able to. It wasn't available. Cost comparison, basically BRBs, I think would have saved $146,000 based on what I was looking at, and side plate could have saved us $1.2 million on the project. That's a huge number. And side plate said that their design services would have been $108,000 this project. So anyway, that's my presentation. I think the point is, moment frames are back, and they've been out since the Northridge earthquake. They've been kind of under fire, but with side plate, pardon me, came out of nowhere. With side plate, some of the other connection styles out there, we have options to use them. It's kind of one of these things that we forget about sometimes, but look for that project where moment frames are the right solution. And if side plate is part of it, you can ask us if you have any questions on the process. We don't own them. We're not part of them, so they're there for everybody's disposal. But we do think that they provide a good service and a good end product. Happy to take any questions.
Do you have any on? Well, a Bartlett, you went with a single bay frame side plate,
I think so.
and
Yeah.
still feel that would be the right answer for that project. Side plate for that one. I'm questioning just.
Yeah. And the problem is that was Colin's project. I think it made its way into this presentation because when I first made that presentation, that was like one of 2 other projects we had done. And I almost took it out this morning because I'm like, I don't know enough about that project. So I do know that the conversation was had, and it may have been just the kind of thing that side plate felt like, hey, we need to get up there more. Honestly, I could understand why a moment frame was important to use if you've got this open cafeteria and it's the only way to get it done. And I think probably we've gone down the road enough now that as we approach side plate on projects, there's definitely projects where they say, yeah, I don't think that we're a good fit for this particular project. And I think if they were to see that one today, they'd probably say that. But at the time, it was like the second one in Alaska. So of course it was a good fit. So yeah, I mean, who knows? Maybe it was still, I don't know enough about the project to tell you why it was selected for side plate.
They've been rules and thumbs, like PRVs was like 3 stories, 1,000 square feet, less than that.
Well, you know, every time we try to set that kind, there's some situations where it's clear that it's going to be probably a good fit. And then there's other ones where we're not sure. And so kind of what we do is we approach them and let them look at it, and they basically will tell us. But certainly a single story building probably is not going to be a good candidate for side plate. 2 stories, maybe, it kind of depends on how big, but 3 stories and up, I would say it's definitely worth, if you're going to do moment frames, it's definitely worth looking into side plate if you've got 3 stories. And we thought like, hey, wacky geometry, maybe that's not going to work. And, you know, I think that the point is like any assumptions that we might have as far as, hey, this might not be a good candidate, turns out those are not always right. You know, we thought for sure the TED project with the parking area that they'd look at that and be like, yeah, you know, they were all about it. They're like, oh yeah, no, and they had other projects that they had done in the lower 48 that were similar enough that we said, okay, yeah, this fits, this works. You know, and we can do the design using our design software, and then they just basically come on board and help us figure out, is this the best layout of the moment frames? And then they do their thing and they design the connections completely.
Got any more questions from the room?
Awesome.
Scott, so.
Uh-huh. I don't know that they did. I've
Problems?
You know, on the one hand, I did look at, you know, personally, I looked at a couple moment frame buildings, but after the earthquake. However, I was not doing destructive, you know, investigation into buildings to look at the moment frames. If they weren't exposed, I didn't. I looked at other things, you know, how much movement did we get? Is there something here that makes me feel that, yeah, we do want to open a wall and look into it? Is there a lot of cracking around windows? Is there, you know, just a lot more movement than I would have expected? But I mean, certainly I can tell you that there are a lot of moment frame buildings that haven't had that sort of like deep look into how did the connections do? Is there any cracking? But one thing that, if you do read on the Northridge earthquake, one thing that contributed a lot to the failures that we're seeing in the moment frame buildings was the practice of basically having relatively non-redundant moment frame systems. They would take this big building and they would put one big honking moment frame on each of the 4 sides and call it good, because that was less expensive than having kind of more spread out moment frames where you incorporate 2 bays or you have 2 on each side of the building. And I don't know that we did that much up here. You know, the biggest thing that you find up here is you've got moment frames with non-qualified connections. There's several medical office buildings and clinics that have HSS columns with sort of like this stop sign plate above and below the beam that welds all around it. It makes this sort of 4-way moment frame. Not at all allowed under the current code, but they did it in every bay. And, you know, we've had several projects where we've opened those up and looked at them and we don't see any damage. So, I mean, that's sort of always the specter that can be out there. Is something damaged? Is something vulnerable? And we just don't know about it. And the reality is that, you know, there isn't enough money in the world to go and look at every single building that was designed under a previous code. And so when we find a glaring situation where we've got a consistent vulnerability, like the wood trusses that we're all super thrilled with looking at, you know, the wood trusses with the snow load, parallel cord metal plate connected wood trusses. That is a consistent, significant, glaring vulnerability in this town. And we're still struggling to find a way to enforce people in any sort of way. We're just struggling to compel people and educate people to look into these trusses, much less force them to do anything about it and pay them. So that's sort of the issue that we have. But I think that if I had to pick one of those to pursue, it would be the wood trusses, not the moment frames. And there just aren't as many of them. I mean, it's like we got some office buildings in Midtown with moment frames, and some medical buildings, but just not really as many moment frame buildings here. I hope that answers your question.
Okay, we got a couple questions online. We got Ken Anderson with R&M. Ken, you're up.
Ken Anderson with Reed Middleton.
Sorry, I read middle.
Unless there's another Ken Anderson that happens to be at R&M, but hey, Ken, long time no talk.
I know, actually, no question. That was just acknowledging that I could hear you at the start of the presentation.
All right.
All right.
Well, and we can all hear you now. Good to hear you, Ken. Hope things are well.
Yep, going well. Thanks.
I did see Brian DeMezas pop up. Do you have a question, sir?
Yeah, I did. Thanks. So I'm a field engineer with Simpson Strong Tie, and I recently started covering Alaska, and I've joined the group here. And so I felt like this presentation was really interesting, and I really appreciated that, Greg. My question would be, have you, I know you kind of showed the yield link system at one point from Simpson. Have you guys utilized that at all? Has there been any differences that you've seen if you have, or I'm just kind of curious. I'm a little bit newer to the area.
Yeah, and I did sort of gloss over that. There was a slide earlier that listed some other available systems, and I know that Simpson's Moment Frame system was on there. It's one of those things that I think that at least my perception is that for a larger steel building, it's more for smaller applications like commercial, maybe even residential, but I might be mistaken. I mean, I may not know enough about it.
Yeah, no, that's no worries. That was the traditional kind of, that's where it came out, is kind of residential and smaller stuff. We've added since then to kind of incorporate some larger steel structures, but I'm happy to talk about that further. I don't need to make this a present. I'm trying to take over. I was just curious because a lot of the benefits are similar. It's just a different method. So I was very interested to just hear if you've had a different experience. So appreciate that.
Well,
thank you.
I would probably just encourage you to get in touch with Nikolai after the meeting, because he's always looking for people to present to the group, and we're always looking for good presentations on new things. And I guess for my own personal understanding, which I will freely admit may not be correct, I'm just not clear how that dovetails into our role as a structural engineer for a product or for a project. And I'd be definitely willing to hear more about that. And so that's one of the things that I really liked about SIDEPLATE, is because it seems like their role dovetails very nicely into our role as the structural designer of record. They come in at the right time when you're trying to lay things out. Then they sit on the wings until you're ready to throw things at them. You have this back and forth, and then it's very clearly delineated, hey, this is our stuff, this is your stuff, this is where the Venn diagram overlaps, and there's good communication and it works well. And so if Simpson's got a system that works the same way or works differently, let's hear about it. So
yeah, for sure. Ours is slightly different, but I think just because SIDEPLATE, they stamp those drawings, correct? Or do you stamp them?
They stamp their drawings. They produce a set of construction drawings that are stamped. Yeah.
Gotcha. Yeah, that would be the main difference there, is that you would stamp the drawings with our products on them.
Okay.
But we can talk more later.
Yeah, for further exploration, I think that'd be an interesting thing to hear about. So, and and maybe you've got some other products too, because I know that there's, if you've got other similar products that sort of work the same way, we could loop them all in together. So
for sure. Yeah.
Thank you, Brian.
Thank you.
Any other questions online? Okay, if not, it is 1:11. We're going to
I went over.
call the meeting at that time. No, thank you, Greg. That was a really good presentation. Enjoy that water bottle. Don't put that where it'll fall and hit you, because it's pretty heavy.
Yeah.
They're also fairly indestructible. I've dropped them down a canyon and found it, and it was still good to go.
Nice. Well, thank you, Nikolai, for putting this all together. And let's not forget the value of organizations like this one. Structural Engineers Association is a worthwhile group to be a part of, not just for these meetings, but for other things that it does behind the scenes and at the national level. And so if there are people that you work with, colleagues or coworkers or others that you feel should be part of this organization to get value from it and to put value in, because it's a two-way street, then get them in touch with leadership and get them on the membership rolls and You touched upon a couple things at the beginning of the meeting. There's things that other states are doing that we're not doing. And some of that can come down to the fact that we don't have as many people, but some of it just comes down to taking that first step before the machine starts really rolling. And so we got some younger people. We're starting to get sort of like a new generation of younger engineers out of college, out of school, or wherever. And let's make sure that the Structural Engineers Association of Alaska is part of their professional profile. And there's other organizations too. I always fly the flag of Alaska Society of Professional Engineers. We take our license for granted. There are states where they're trying to get rid of professional licensing, and so it takes vigilance and it takes work. So, and it takes dues dollars. Thank you.